Hi, and welcome back from the CAOS team at Politecnico di Milano. In this video, we will see an example of usage of the CAOS framework with a demo application regarding vessel segmentation. Writing a vessel segmentation is an important process in biomedical applications, as it is used as input for a high number of diagnosis methods. As an example, it is used for checking vessels in a retina in order to diagnose illness such as diabetic retinopathy. This family of algorithms is computationally intensive, and an implementation on FPGA would benefit both in terms of performance and power consumption. Let's have a look on how we could optimize such algorithm with the CAOS framework. We just need a web browser in order to use the framework. Once connected to the web interface, we need to select the Project Manager tab in order to start. The Project Manager tab allows the creation of a new project or the load of an existing one. For this example, we are going to create a new project. After clicking on the new project, the IR generation phases start. For each phase, we will have a new tab where in the right corner of the screen we can see if it is still in progress or it has been completed. The IR generation phase starts from the source code and extracts the list of functions that composes the code. Hence, we need to provide the archive file containing the source code of our application. Another file we need to provide is the program description. The program description is a JSON file, and in this file we have all the information regarding what is the language of the source code that we are providing, as well as the supported compilers and the arguments needed for the compilation. Let's specify our program description JSON file. At this point, everything is set, and we can click on Run IR Generation in order to start this phase. As soon as the phase finishes, we have a message from our program that says that IR generation phase is completed. After closing the message, we can see that the program is showing a program static call graph. And a list of identified functions. We can click on a function and see the related code. In the next releases, it would be possible to directly modify the code of the particular function from the web interface. Now, by clicking in the top right corner on Complete, we can terminate the phase and then move to the applicability check one. This phase expects a JSON file called the architecture description and a selection of one or more of the architectural templates among the available ones. As of now, the only available architectural templates are SST and the master slave paradigm. Then we click on Save, and like in the previous phase, clicking on Run, we can start the computation and wait until we receive the success message. Now the program shows the validation results for each template chosen. In our example, we can see how our code is not suitable for the SST architectural template, but it is instead possible to implement it using the master-slave paradigm. In the table, we can see, for each function, if the particular function can be, or not, implemented in hardware, and the reason is provided. The check that is made in this phase excludes the functions that are not implementable in hardware in a specific architectural template, due to unsupported features, as for instance, unsupported function call. In the example, the only function that is implementable in hardware is the match filter one. To move in the next phase, we need again to click on Complete and then on Profiling. Note that at each step of the flow, you can come back on the previous step by clicking on the name of the phase. Then, if we want to modify something, we need to click on Edit in the top right corner. In this case, we have an alert from the program that is asking us if we want to really modify this phase, as we already moved to a successive one. In case we click on Yes, the program will invalidate all the successive phases, as they rely on the one we are modifying now. Let's come back on the profiling phase now. Here, we need to provide to the program a profiling dataset. First, let's give a name to the dataset. And then, let's provide the archive with the necessary files. Now, we need to give to the program the command line arguments that are necessary to run the test. Now that we have a dataset loaded, we can start the profiling on the particular dataset. The profiling provides, for each function, the percentage of time spent within the function itself and the percentage of time of the function plus the time of all the subfunctions called. Thanks to this information, we can understand what function is the most compute intensive, and then we can have more information on which function is more convenient to optimize. Now, let's complete the profiling phase and move to the partitioning. In this phase, we specify, for each function implementable in hardware, what function we want to leave in software and which one to implement in hardware. We can do this by using this drop-down menu. Here, we have only the match filter function that is implementable in hardware, and as we want to implement exactly that function, we click on Hardware and then on Run Partitioning. This button starts an automatic check that analyzes the function selected to be accelerated in hardware and automatically excludes the one that does not satisfy particular checks made on the profiling results. Now that the partitioning is done, we have our functions to optimize. Let's move to the next phase that involves functions optimization. This phase shows for each architectural template the code that we can optimize. We click on Initial Code and run Start Optimization to start the process. This process involves more than one step. The first one is the stated code analysis. As of now, the analysis is implemented so that it checks the candidate functions and provides values regarding the average, best, and worst latency. The successive phase is called hardware estimation. Here, an estimate of the hardware resources consumed on the FPGA board is provided for each function that we want to accelerate. In this particular example, our match filter function consumes 1 VRAM, 8 DSPs, 1106 flip-flops, and 1300 slots. Once we have the hardware estimation of our kernel, we can do our performance estimation. The performance estimation phase provides information regarding function performance estimation and the suggested optimizations. On the left side, we can see the performance estimation for the current function implementation. The execution time is 997 seconds with a clock frequency of 100 MHz. While on the right side of the screen, we can see the performance estimation for the pipelining optimization. The execution time is of 90 seconds with a clock frequency of 100 MHz, with an area consumption of 0 VRAMs, 38 DSPs, 2,674 flip-flops, and roughly 3,000 LUTs. After the performance estimation, we can move to the code optimization phase. The optimizations here has been applied, and the framework provides us with information regarding for which function, in this case the match filter, it applies the optimizations. Now we can move to the next phase. In this phase, we can regenerate the IR and then conclude the function optimization phase. At this point, we have two folders. The first one contains the initial code that we just optimized, and another one, called Optimize, where there is the optimized code. At this point, we can pick up one of the folder and start the optimization process again, or we can download a version of the code on our computer to further investigate the code. Otherwise, we can conclude the function optimization phase and go to the next one, the implementation. By clicking on Run Implementation, we are actually doing the implementation on the board. As it ends, it provides us with an archive. By clicking on the archive, we are able to download it, and as it is observable here, inside the downloaded folder, we can find the bitstream and the HDF file for the specific FPGA. Finally, we can complete the phase, and the flow has completed. Now we can take our project and save a version of it on our computer, so that if we want to modify the project again in the future, we can take the project and load it back in the framework. So, thanks for your attention from the CAOS team. If you need any further information, please do not hesitate to contact us.